Welcome to section 8.4. Now that we've had an introduction to logs and we know how to switch between log and exponential forms, we're going to be solving equations that have logs in them. In today's video, we're going to be looking at two different solving methods. First solving method you can see at the top is switching forms. So switching from exponential to log or log to exponential. And then eventually we're going to talk about option 2 that you can see at the bottom here, which is log equality. Let's just jump right in. So option 1, we are going to switch forms. If we look at example number 1, we see we're in log form. We don't know how to solve this right now. This isn't helpful to us. We're not particularly comfortable with log form, so it might be helpful to switch to exponential. If you remember from yesterday's video or a few days ago, we used the acronym BAE, so base, argument, exponent. So switch forms, we get 6 to the x equals 1 over 36. Okay, this we've solved before. This is one of those exponential equations where we get both sides in terms of the same base. So 6 I can't simplify at all. I'm going to just leave that as 6 to the x. 1 over 36, though, is 6 to the negative second power. Okay, both sides are in terms of the same base now. So now I'm allowed to equate those exponents. And in this case, I get x equals negative 2. So in the 8.3 video, I told you I was very picky about the x, not including x in your answer. In this case, though, x was in our original equation, so it is okay to say x equals. Example number 2, we're in log form again. Again, might be helpful if we switch forms. So we have base, argument, exponent. So switching forms, we get 36 to the power 3 over 2 is equal to x. So remember that A stands for argument or answer. Okay, x is alone, so what we need to do is simplify that left side. You may have seen at the top of the notes there was a no calculator symbol, so we shouldn't be using a calculator on this. We need to figure out what 36 though to the power 3 halves is. This is a little bit of a throwback to another form. So this is called exponential. Hopefully we remember radical form. So 36, which is the base, goes underneath the root. That 2, the denominator, goes out in front, and then to the third power. Okay, so square root of 36, so this part, square root of 36 is 6. So I get 6 to the third equals x, and I will tell you that 6 to the third is 216. Again, it's okay to write x equals because x was in our initial problem. Okay, let's try one more, and this is example number 3. Again, switch forms. So we get x to the power 3 over 2 is equal to 27. So we need to get rid of that 3 over 2. That's a power. So I have to figure out what power do I need to take this to get rid of it. Well, it's actually going to be the reciprocal power. Okay, and here's why. I'm going to end up multiplying across a power to a power. Remember, we multiply them. So I get x to the power 6 over 6 is equal to 27 to the power 2/3. Well, x to the 6 over 6, that's just x to the first. So anytime we need to get rid of a power, we do the reciprocal power. And that should make sense. If you have a square root, you square both sides. That's the reciprocal power. So now we just need to simplify that 27 to the 2/3. Again, I do not want us using a calculator for this. This is really the cube root of 27 squared. Cube root of 27. So this part right here. Hopefully you know that. If you don't, break down the 27. You get a 9 and a 3, a 3 and a 3. Because of that 3 out in front, I'm looking for cubes, or a grouping of 3. So I get 3 squared, which is 9. Okay, so that is definitely a review from chapter 7. So if you need to look back at chapter 7 or chapter 6, it's one of the two, please do that before going on. This last example now is one that I want you to try. So this is an example that you are going to try on your own. Pause the video, give that one a try, and come back when you are ready to move on. Okay, hopefully you gave this one a try. I'm going to let you know you should have gotten x equals 4. X equals 4. Now, I will tell you, I'm not going to give you credit for this video unless you have that problem done. So make sure that you do that problem. If you got that one wrong, take a look back and see if you can fix it. If you are ready, let's keep going. Okay, so option 1 was switching forms. Option 2 is log equality. For most problems, you don't get to pick which option you're going to use. You're going to pick the option that applies. So let's jump into the property of equality for logs and see some examples, and we'll talk about how to know which method to use. Property of equality for logs. Log base b of x is equal to log base b of y if and only if x equals y. What's really important that I want you to notice here is those bases are the same. If the bases are the same, and only if the bases are the same, then the arguments are going to be equal. So that's really, really important. This property of log equality is only going to apply if we have the same base. So if we look at that quick little example, it says if log base 5 of x is equal to log base 5 of 8, then what does x equal? Well, again, our bases are the same. We have a base of 5 and a base of 8, which tells us our arguments are equal. Okay, so if we look at examples 5 and 6. Example 5, 2 things I'm going to notice. First thing I want to notice is that there's a log on both sides. Okay, that is different from the examples 1 through 4 we did at the top. Examples at the top, there was only a log on one side. Now we have a log on both sides. What we also notice is that the arguments are equal. Not the arguments, the bases. So we have a log on both sides. The bases are the same. What that tells us is that our arguments have to be equal. So I get x squared minus 4 is equal to 3x. This is what we need to solve. This is another throwback. So a lot of these things we went over in class, I said we would be seeing them again. This we've solved before. This is a quadratic. If you remember, you gotta move everything to one side. So I'm gonna subtract 3x. So I'm set equal to 0. How do we solve a quadratic? Well, we have a few options. Completing the square, factoring, quadratic formula. I'm gonna try to factor this. So we are looking for two numbers that multiply to -4 and add to -3. Multiply to -4 and add to -3. That's going to be -4 and +1. Setting both of those equal to 0, I get x equals 4 and x equals -1. Okay, we have an extra step here. I don't know if we've talked about this before, but the argument of a log always has to be positive. So that's really important. Let's write that down. Argument of log is always greater than or equal to 0. It's always going to be positive. So we have to make sure our values of x in the domain here. In the domain, okay, if I plug in 4 to this 3x, for example, am I going to get a positive number? Yes, I am. What happens if I plug in -1? No. If I substitute in -1, I would get a -3. It does not make sense to have a negative argument. +1 does make sense, though. So our only possible answer is x equals 4. Substituting that into the left side now. If I do 4 squared minus 4, so 16 minus 4, I would get 12, which is still positive. So it's really important for these. You always have to make sure your argument is positive. The argument can never be negative. So you're going to have to substitute your value into both sides, both logs, and make sure you end up with a positive argument. Okay, I know that was a lot, so let's go through another one together. Example 6, we notice there's one log on both sides. Okay, so that's different from what we did above. We also notice, like before, the bases are the same. Again, if the bases are not the same, there's nothing we can do. So we always got to make sure bases are the same. If I have one log on both sides, bases are the same. Again, that tells us our arguments are equal. So we get x squared minus 15 is equal to 2x. Quadratic, we're going to factor it again, so move that 2x over. I'm looking for two numbers that multiply to negative 15 and add to negative 2. That's going to be minus 5 and positive 3. Setting both of those equal to 0, I get 5 and negative 3. Okay, so we need to substitute into both arguments, so both this 2x and this x squared minus 15, and make sure that we get positive arguments. If I substitute negative 3 into that 2x, I'm going to get negative 6. Can't have a negative argument. If I substitute 5, though, I get 10, which is good. Make sure 5 works in the other argument. So I get 5 squared minus 15, so 25 minus 15 is 10, which tells me x equals 5 does work. Okay, a word of caution here. We cannot just throw out every negative answer we always get. So some people like to assume that a negative answer isn't going to work. That's not always the case. If you have a negative, check. Check and ask yourself, does this work? Don't just automatically throw it out. Okay, if we're going to flip the page now and you have an example to try. Right now you are going to try this example at the top, the one that says you try. So I want you to pause the video, try this one on your own, and come back when you are ready. Good luck. Okay, hopefully that you try example went well. We will go over it in class tomorrow. We have 2 more to do. Let's look at example number 8. What I want us to notice about example number 8 is there's a log on one side but not the other. That means something. So what some people want to do is they want to set this x squared minus 2x equal to 3. We can't do that. There's not a log on the other side. We can't do that. Not a log on the other side. So in a case where we have a log on only one side, it's going to be similar to the first few problems that we did, where we're going to switch forms. If there's a log on one side only, you're going to need to switch forms. So we have base, argument, exponent. So we get 2 to the third is equal to x squared minus 2x. 2 to the third is 8. Now this is a quadratic that we have to solve. So I'm going to move that 8 over. So I get x squared minus 2x minus 8 is equal to 0. And now I'm going to factor. Okay, looking for two numbers that multiply to 8 and add to negative 2 is negative 4 and positive 2. Setting both equal to 0, I get 4 and negative 2. Okay, check. Make sure these make sense. We only have one argument that we need to substitute into, this x squared minus 2x. If I substitute in that negative 2, because that's the one I'm most concerned with, I'm going to get negative 2 squared minus 2 times negative 2. So this is 4. Be careful. Negative and a negative becomes a positive 4, which gives me 8. So that one actually works. That negative works. Like I said, you can't just throw them out. If we substitute in 4, we get 4 squared minus 2 times 4, 16 minus 8, which is positive. That's good. So this is a case where both actually work. Or both work. So again, you cannot just throw the negatives out. You can't just throw the negatives out. You need to substitute into your arguments and make sure that both work. Okay, last problem. Log on one side. Log on one side, we're not using property of equality, so we don't get to say x equals 32, done. If there's a log on one side, we're switching forms. So we get 4 to the x equals 32. 4 to the x equals 32. Okay, so this is one of those examples that we did at the beginning of the chapter. We need to find a way to write both sides of this equation in terms of the same base. So can we break down 44? Yes. Can we break down 32? Yes. I will tell you that 4 is 2 squared, and 32 is 2 to some power. So I'm going to have you finish that one, and we will go over it when you come to class tomorrow. This is the end of the required portion of the video. If you want to do a few extra examples together, which I think is a great idea, stay on. If you're confident that you understand this material, then finish this last problem and you may stop the video. So let's look at a few extra examples. Example number 10, we should notice there's a log on one side, not on the other. Log on one side, not on the other. If we have one log, we're going to switch forms. So we have our base, our argument, our exponent. We have 4 squared is equal to x squared minus 6x. So 4 squared is 16. Okay, at this point, we need to move everything to one side. So I have x squared subtract 6x subtract 16. Okay, so we are looking for two numbers that multiply to negative 16 and add to negative 6. So that's going to be negative 8 and positive 2. So I get 8 and negative 2. Now we are not finished. We have to make sure these work. In other words, that our argument is still going to be positive. If I plug in negative 2, I get negative 2 squared minus 6 times negative 2. So I get 4 plus 12, which is positive. If I substitute in 8, I get 8 squared minus 6 times 8. So 64 minus 48, which is positive. I don't really care what number those equal. What I care, though, is that I end up with a positive argument. Hence, both of our answers work here. So again, like I've said a few times in the video, don't just automatically throw out those negatives, because oftentimes they do work. If we look at example 11, this one is different because there is a log on both sides. There's a log on both sides and the bases are the same. Log on both sides and the bases are the same. So I can set my arguments equal. So I get 4x squared subtract 3 is equal to 11x. Move that 11 over, so I get 4x squared minus 11x minus 3 equals 0. Okay, this one's different because we have a 4x squared. So our factoring is going to be a little bit more complicated. We could always do the quadratic formula as well. When you have a number in front of that x squared, though, that's anything other than 1, you gotta split the middle. Gotta split the middle. So I multiply the 4 and the negative 3, and I'm looking for two numbers that multiply to negative 12 and add to that number in the middle, negative 11. That's going to be negative 12 and positive 1. So if we remember, split the middle, we are splitting the middle term in terms of negative 12 and 1. So I get negative 12x plus 1x. If you remember, order doesn't matter, so I could put the 1 first if I wanted to. Now verify, does that make sense? Yes, negative 12x plus 1x does give me negative 11x. So then that first term comes down, that last term comes down, and now we factor both sides. So we factor the GCF on the left side, factor the GCF on the right side. On the left side, I factor out a 4x, and I'm left with x minus 3. On the right side, my only GCF is a 1, and I'm left with x minus 3. At this point, do a mental check. Am I on the right track? If I am, those parentheses should match. Okay, so x minus 3 becomes one factor. Stuff out in front becomes the other factor. Setting both equal to 0, I get 3 and negative 1/4. Now we got to make sure our arguments are going to be positive. So we got to go substitute back into the 11x and the 4x squared minus 3. Right away I can tell 11x, if I substitute in x equals negative 1/4, I'm going to have a negative argument. It'll be a negative 11/4. Doesn't really matter what the value is. What matters is that it's going to be negative. If I substitute in 3, 11 times 3 will be positive. If I substitute 3 into the left side as well, I'm going to get a positive number as well. So in this case, our 3 works. So again, you really have to check for each problem. In example 10, our negative worked. In example 11, our negative didn't. Always got to pay attention to those arguments and make sure the argument is positive. Last one, example 12. Again, log on one side, not on the other. Log on one side, not on the other, so we're going to switch forms. I get x to the 4/3 is equal to 81. Okay, I got to get rid of that 4/3. If we remember from way the beginning of the video, you're going to raise to the reciprocal power. So that left side, that's really x to the 4/3 to the power 3/4. If I multiply a fraction by its reciprocal, I just get 1. So I get x equals 81 to the power 3/4. That's what I have to simplify. If I switch to radical form, that 4 is what goes outside, so I have the 4th root of 81 to the 3rd. Some of you may know the 4th root of 81 in your head, some of you may not. If you don't, we're going to break down that 81. So we get 9 times 9, 3, 3, 3, 3. Some of you are going to say 9. The 4th root of 81 is not 9. Remember, 4th root means I need a group of 4. 4th root means I need a group of 4. So the 4th root of 81 is actually 3. And then don't forget that cube root. Not cube root, that cubed power. So finally, 3 to the 3rd gives me 27. Don't need to check the argument here. The argument's 81. It's already positive. Okay, so I know that was a lot. That was a lot of review from other chapters. Hopefully it jogged your memory, though. If you have any questions, please write them down so that you can ask in class, or you can send me an email.